think it's time to get started. Hello, everybody, and welcome to another IRENA online seminar. My name is Panos Gastis from Los Alamos National Laboratory. And today I'm very pleased to introduce you to Dr. Chiaki Kobayashi, who is an associate professor in astrophysics at University of Hertfordshire in the United Kingdom. Dr. Kobayashi specializes in galaxy formation and evolution. And today is going to talk about galactic archaeology and the origin of the elements. Just a short note before we start. If you have any question during the presentation, feel free to unmute your microphone and ask directly the speaker, or you can also type the question in the chat. We will also, of course, have some time for questions at the end of the presentation. So Dr. Kobayashi, you can start the presentation whenever you're ready.
Thank you. Thank you very much for the introduction. So it works. Okay, I think, oops, slightly wrong behavior. I think you can see some thing moving on your screen. I'm never sure how it works on a Zoom meeting. So I would like to show here that how chemical enrichment, evolution of elements are dramatic in the universe. Here I'm showing the galaxy grow in a cosmological context from small galaxy to massive galaxy. And at the same time, the distribution of elements dramatically changes as a function of time. Today, I'm going to focus the method to study Milky Way called galactic archaeology and the origin of the elements. So galaxies should form from the cosmological initial condition, which is observed now, the above one, with a cosmic microwave background. But to make this actual beautiful image of galaxies, it's actually not easy because we have to solve a lot of unknown processes such as star formation and then impact after the star formation to the galaxy environment. However, once we start form in a galaxy, we actually relatively well know what's going to happen after that, thanks to the long-term collaboration between nuclear and stellar astrophysics. Okay, the stars formed from this collapsing gas cloud. If the formed stars are massive, let's say more than 10 times the solar mass, those stars explode as a supernovae at the end of their life, which produce a lot of oxygen, magnesium, so-called alpha elements, and a bit of iron peak elements as well. Because they are massive stars, the time scale is short, million years or so. Low mass stars can produce quite a lot of heavy elements, iron peak elements, if they are in a good binary system. By a thermonuclear explosion, it's a different explosion and different type of supernova called 1A. Because they are low mass stars, also there is a time scale for the binary evolution. The time scale is usually giga-year or so, longer than the first one. Single low mass star can produce a bit of elements during a symptotic giant branch phase, but the production element is limited to carbon, nitrogen, and slow neutron capture elements. They are low mass stars, so time scale is also long. Massive binaries can cause neutron star mergers, and in that case, rapid neutron capture elements are formed. This is proved now by the recent detection of gravitational wave event. So therefore, in a galaxy, not only the total amount of heavy elements we call metallicity, but also elemental abundance ratio we usually take relative to iron. These quantities evolve as a function of time. So we can use all of these informations as fossils to understand the evolution history of the galaxy. So this approach now became very popular and called galactic archaeology. So there are lots of galactic archaeology surveys ongoing. The big one is with Gaia satellite missions, motion of 1 billion stars are measured. With a new technology called asteroseismology, it's now possible to estimate stellar ages quite accurately. This is quite new results. And our nuclear astrophysics interest is the next one. It's also possible to measure detailed element abundances from 1 million stars of a large number of spectra using multi-object spectrograph. Lots of spectrographs are being developed in the world. And then the color highlighted ones are those I am participating in. And then the new mission also planned on a Hawaii Island as well. So therefore, we are really getting a huge amount of data set of chemical and dynamical evolution of our Milky Way galaxies. So we would like to use them to understand the history of the Milky Way. When I say Milky Way, it's actually quite complicated. So this is actually images of that Gaia satellite detected. So you can see some structures here. So central part is more dense, so that's called bulge. And also the very quite thin disk you can see on the plane. Plus there is a diffuse component that's called thick disk. And how the above and below the plane, it's not empty. So there are lots of stars, mostly old metal poor stars located there, and that's the galactic halo. With this detailed observation, now we see a few satellite galaxies, small one, much smaller than the Milky Way itself, but many of them exist around the Milky Way, plus the debris of these small galaxies, some streams, the Sagittarius stream just below and above that around here, also observed. So what was the main physical process of each component? We would like to know this to fully understand the history of Milky Way. And then to do that, the fossil record are the kinematics and chemical abundances of stars in each component. In terms of models, we use a galactic chemical evolution model. So I'm briefly going to explain this. This is only one equation I'm going to show today. It's also called the one-zone model because it assumes that the interstellar medium in the system we consider is instantaneously mixed. It's very classical model. It started from the 70s. The equation is just this one. So we integrate the time evolution of a total amount of heavy elements in a gas phase. Z is the metallicity, so that's mass fraction. So if you times by gas fraction, that becomes the metal mass. So this quantity increase if there are metal ejection from stars or supernovae. The first three terms, metal ejection rate, highly depend on nucleosynthesis yields, plus also how many massive stars we have compared to low mass stars, that's called initial mass function. And type 1 supernova is uncertain, the modeling is also uncertain, plus more fundamentally, nuclear reaction rate that comes into the first one, the nucleosynthesis yield. If we form stars from this enriched gas cloud, the metals are trapped into the inside the stars. So metal mass actually decrease proportional to the star formation rate. Also, if there is some gas inflow from the outside of the system or outflow from the enriched system to the outside of intergalactic medium to the outside of the galaxy, again, metal mass can be increased or decreased. So the last three terms are galactic terms. So those are ideally given by hydrodynamics, purely from the physics. And this is very complicated and chemical enrichment becomes very inhomogeneous in this case. However, in a classical one-zone chemical evolution models, these last 3 terms are given with a very simplified analytic formula. But they are still very useful to discuss this, to test the input nucleosynthesis yield and so on. There is also intermediate approach to still simplified in terms of galactic terms, but there are a few attempts to include inhomogeneous enrichment in a stochastic way. And then there are also such models. Also, a few people are working using this type of model as well. So in my talk, I'm gonna use only 1 and 3. So the half of my talk is based on very simple one-zone model to constrain nucleosynthesis yields. The last half of my talk, I'm gonna show lots of simulations and then the images using our chemodynamical simulation of a Milky Way-type galaxy. So let's start. We updated recently with my very close collaborators. Many of you, I think, will recognize. We are actually long-term friends as well. Often we have some holding wine and so on for a long time. We have updated our chemical evolution model. We included new solar abundances, new initial abundance. That means Big Bang nucleosynthesis abundance, and also type 1 supernova yields also fully updated. There is a missing area just above AGB stars. It's actually very difficult to solve this stellar evolution at this mass range. That's called the super AGB stars. We have included some yields from these mass ranges as well now. And then I will talk about this more, but so-called we included phased supernova as well. I will explain more in a few minutes. More importantly, we extended the elements. We cover all stable elements now up to rhenium, including slow and rapid neutron capture processes. Let's start from the nucleosynthesis yield. So this figure shows how much mass of element should be produced from a star with a given mass on the x-axis. Lone star, it's actually plotted, the line is plotted, but you don't see at all. So the different color shows different elements. For example, oxygen production is very negligible, up to 10 solar mass or so. Above that, the quark supernova release oxygen that is actually formed during hydrostatic burning of the star during the evolution, but the oxygen is released at the end of the stellar life. You can see the line goes up to right. So that meaning more elements are produced from more massive stars. This line probably continues to 20 or 40 solar mass or so, but above that, probably stars are so massive that are all produced metals will fall back to the black hole, but that is uncertain and many people are working on. I'm not going to talk about the very massive stars so much today, and let's focus this around up to the 40 solar mass or so today. Supernovae are observed, quark supernovae also observed, but it's actually very difficult to explode them in a computer. About 10 years ago, nobody succeeded. About 20 years ago, nobody succeeded, but gradually we see very beautiful simulations of quark supernova. The mechanism, explosion mechanism is still debated. Also, it's not fully consistent with the observational data. Observational data we can have for individual quark supernovae are following. So we can we can measure the luminosity, that's directly the mass of ion, because the supernova can shine with the radioactive energy of this nickel-56 close to ion. So the change of the luminosity can give us some information. Plus spectral information also tells us the motion of the ejector. Combining these two, it's possible to estimate the initial mass, kinetic energy, and the ion mass. So that's what we did in a Japanese group. for a long time, and then we got this result. So if we plot the initial mass of the star on the x-axis, and then the ejected energy, this is indirect. This is estimated from these observations. We got this result. So that the famous 1987 the one happened in a large magnetic cloud. That's have the ejected energy is 10 to the 51 erg. In a community, it became the unit of the energy 10^1451 erg. And below that, the ejected energy looks like very much constant, but above that, there is two sequences you can see. One is increasing, and then the other probably decreasing trend. So the more bright one is very important in terms of the enrichment of galaxies, because they produce quite a lot of iron in a short time scale. So we named them hypernovae, and I include this contribution in my chemical evolution model as well. How many stars actually go to hypernova is uncertain. So I set this in a fluid parameter in my chemical evolution model, and it varies as a function of time. This is just assumption, but it's not unreasonable, because in a metal poor area, it may be possible to have this large explosion by somehow, because of the loss, the smaller amount of angular momentum loss or something. And then another feature is the failed supernova. First of all, theoretically, it's possible to explode stars with neutrino-driven mechanism, but that's possible up to 20 or 30 solar mass or so. Above that, still it seems very difficult to explode stars with this mechanism. Observationally, people look at the location of supernova and then go back to the archive of HST imaging, and then can identify which was the actual progenitor and then measure the mass. And then no progenitors found above 30 solar mass or so. So both theoretically and observationally, it seems a lot of stars just don't explode, so it's failed supernova. This has been suggested for a few years already, and then now I also included this in a parameter and constrain this fraction from chemical evolution modeling. So the best parameter set is like this. So I'm going to talk more about electron capture and magnetic rotation supernova later, the middle part. So if in terms of chemical enrichment, chemical evolution models, the best best model is if supernova continues to explode up to 30 solar mass, and then below that can become failed supernova if I keep having hypernova at this 20 to 50 solar mass or so. And then I still need 50% of very massive stars, more than 20 solar mass, to explode as hypernova. Otherwise, it's not possible to explain elemental abundances as observed. Let's switch to the second type of supernova. That's type 1A supernova, a thermonuclear explosion in a binary system with carbon, oxygen, white dwarf. That's all we know. And then there is a long debate. Either the progenitor system is single degenerate, where there is only one white dwarf, or double degenerate, two white dwarf, and they merge. This debate is very long term, and the situation gets just more and more complicated. And then now the focus is what is actual explosion. So if the mass accretion triggers the explosion is likely to be near Chandrasekhar solar mass. So they call the Chandrasekhar mass explosion. And then there are a couple of reasonable explosion models, deflagration or delayed detonation models. And then there are nice simulations as well. On the other hand, if the simulation shows that in the case of merger of two white dwarfs, explosion is more like subchandra mass explosions. So in a single dinner scenario was criticized a long time because there are a number of problems, and one of them was this companion star, which supplies the mass, has never been observed. But that story is now just changed. This is a bit rare type of supernova. But anyway, one companion star have been detected now. So there is at least one single generated system in the universe. We have recalculated nucleosynthesis yield for both Chandra and subchandra models in this new paper with Japanese group plus Shinchi Leon. He is now in Caltech in the US. So this is a cartoon we used for the press release, but actually we have, the Shinchi has simulated 2D hydrodynamical simulation of the explosion of this white dwarf. And also he, as a post-process, he calculated nucleosynthesis yield, and then as a function of initial mass and metallicity. I included them in my chemical evolution model, and we constrained. So we found, well, this is already indicated by also the group in Germany as well. In a Chandra-Sekar mass explosions, it's possible to form quite a lot of manganese in this very high density, high temperature area. But in a subchandra-Sekar mass explosion, it's not possible to produce manganese as observed. So this is a big problem. And in the following my talk, I will use only Chandra-Sekar mass explosions. And I'm going to show quite a good fit from now on, but with including subchandra-Sekar mass explosion, the all fits just become worse. This is the most important figure in a chemical evolution. So I'm going to spend a few minutes to explain this. This is called alpha to ion FeO by chirylation. So you see the observation data and the model lines here. And then you see the data located above, so the high value and almost constant. And that's because a constant fraction of type 2 supernova consistently produce more oxygen than alpha, than the ion. So the alpha to ion ratio, oxygen to ion ratio stays positive value. But at one point, type 1a supernova switch on, and that shows the decreasing trend. At the very, very beginning of the evolution, so nothing happens. So that's called the population tree stars, and we don't know what they become. Probably it depends on the mass and rotation. Anyway, the first explosion we can see only through the abundance pattern in an extremely metal poor star. So that's the stars located below FLH minus 3 or so. The normal halo stars, that's called population 2 stars, are enriched by normal type 2 supernova. And then, as I mentioned already, alpha 2 ion is positive. After type 1a supernova occurred, the abundance ratio, oxygen to ion ratio decreased to become 0,0. That's solar ratio by definition. And those are population 1 stars, usually located on the thin disk. So in a simple galactic chemical evolution models, time goes from left to right. But later on, I will introduce inhomogeneity enrichment. In that case, time metallicity conversion it will be mixed up later on. So roughly speaking, so left side or earlier time is older age. So that's have high alpha population. On the other hand, right-hand side, young age stellar population tends to have low alpha population. So in a galactic archaeology surveys, often old age and high alpha, those two words are used in the same way because of this alpha to ion relation. Neutron-capture elements, that's the new thing we expanded now. So AGB stars is actually, this is observation. It's not a point star. It's nice, very nice image is observed now with ALMA. my collaborator Amanda Caracas and Maria Lugaro both have been calculating nucleosynthesis yield, S-process yield in AGB stars. So I'm using their calculation results. Electron capture supernova, that's also observed image of this candidate of electron capture supernova. And they are suggested for the site of a rapid neutron capture process, but it's likely that the ejector is not enough neutron rich, therefore it's not possible to synthesize very heavy R process element in this channel. Neutron star merger, that's the one detected with gravitational wave and followed by astronomical transient kilonova and also short gamma ray burst. The yields also have been calculated using very sophisticated simulation with GR by Shinya Wanajo in Japan. So I'm using their yield in this calculation. How many those stars, those event neutron star mergers can occur? That's also a big question, and there are a lot of people working on that using binary population synthesis. And I'm using one of the predictions from binary population synthesis when I count the number of the event in electron in my chemical evolution model. So the last one is not observed image. This is computer simulation. We don't have direct detection of this supernova yet in a real universe, but we see quite beautiful image in a computer. So that's a supernova driven by magnetic field and fast rotation and like jet-like explosion. So in this study, we wanted to avoid empirical relations as much as possible. So it is uncertain, but there are theoretical predictions in the community. So we try to get theoretical prediction as much as possible, and then let's see how the chemical evolution model shows. So the order of yields I'm using theoretical predictions. In some cases, only one mass of a neutron star merger, mass combination of neutron star merger is calculated, but I'm applying one set of yields to all neutron star merger events. There is such effect, but let's stick to the theoretical prediction now. So I'm showing one by one now. So those are all the elemental abundance ratio evolution of neutron capture elements in the x over phi plane, and the x-axis is the same metallicity. Y-axis is the ratio relative to ion. So blue line is the prediction only with a slow neutron capture process from AGB stars, and then most of them just cannot be enough produced by AGB. Exception is, we know this already, barium, lanthanum, and so on, plus lead is enough produced already only by slow neutron capture process. If I add electron capture supernova, the very massive end, there is no change at all, but this light element among neutron capture elements, strontium, yttrium, and zirconium, they are quite already well matched with this observation. So these black and gray points are the observation data. Elemental abundance is measured in stellar spectra of nearby stars in the solar neighborhood. So the another site of R process is a neutrino-driven wind that should occur during quite a lot of quark collapse explosion. But if I include them, at least with this yield set, again the Shinya Wanajo's yield, so it will result in overproduction of some of the elements around here. So we found that it's actually better not to include this neutrino-driven wind extra one. So let's remove this. And then plus electron capture supernova, if we add the neutron star merger, the difference is actually very small. The sum of the elements, thorium and uranium, can appear now. The line appears now, but not enough. let's add black hole merger, black hole neutron star merger as well. In that case, the rate can get slightly higher, but not totally enough. Plus, first of all, the absolute abundance is not enough. And secondly, europium, let's look at europium. There are already very high value of europium to iron ratio at low metallicity. But model is still very low. So it's very difficult to explain the high value of europium only with this neutron star or black hole merger. However, if we include hypothetical, but a new magnetorotational supernova contribution, it's possible to explain elemental abundance of many elements self-consistently. I mean, as I said, we include theoretical prediction. There are uncertainties, but in each component, nuclear physics is solved self-consistently. So we can believe some elements are okay, some other elements are okay. So that's, we can believe this result. And then some points, these are the compilation, I think, all elements that have some detection of elements, even at very low metallicity here. So the gold detection is also here. It's actually very difficult to measure gold in a stellar spectra in a metal poor stars, and only HST can do this. And there are only a few stars measured there. Then in this paper, we showed this element, the new periodic table showing the origin of elements in a different color. So that's the, I think the figure you're familiar with from starting from hydrogen and then ended up uranium. And for each little box, there is a time evolution here. So it starts from time 0 and then now 13.8 in cosmic time. And then dotted lines are the age of the sun. Okay, so I am hoping to get this dotted line, crossing point of the dotted lines. That's perfect. For example, some elements it's very good. So like oxygen and iron goes to this dotted line, so that's perfect. Manganese as well, that's perfectly reproduced. Some are off. So this y-axis is actually linear abundance. So there are some mismatches, but actually not so bad. So let's look at the color now. So the black is for Big Bang nucleosynthesis. As we know, Big Bang can produce only the elements up to lithium. So it's black out. Some of them are trapped inside the stars, but they are released when they die. So it's colored with blue and green, that meaning the hydrogen is trapped inside the star, but released by mass loss when they die. So that's the meaning. As I mentioned earlier, carbon and nitrogen, you see a quite large green contribution. It's half of carbon and 70% of nitrogen come from AGB stars. Quite a lot of strontium, yttrium, zirconium, plus most of barium and lanthanum, plus lead are produced by AGB stars. Blue is quark collapse contribution. I included electron capture and magnetorotational supernova, all of them into this quark collapse supernova contribution. So you see quite a large amount of our process elements come from this quark collapse supernova, mainly from the magnetorotational supernova. 1A is important for the iron peak elements and manganese that I highlighted already earlier. The contribution of neutron star merger in this calculation is actually quite small. Some elements were better produced by neutron star merger in the particular nucleosynthesis yield are used, but the contribution is in general very small. And then when I showed this figure in a press release, quite a lot of people got interested in, but not this full picture of a periodic table, but mainly on the gold. So lots of news coverage says missing gold problem or the gold mystery. I'm just showing some of the, yeah, people's interest is really gold. And gold I could not reproduce this. The gold is here. It's much underproduced in the model than the observation. Small points in the observation rate of metal poor stars, and then this dotted line is the solar ratio, and compared to the solar system, the gold production in the universe in my model is very small. Although I included both magnetic rotational supernova and the neutron star mergers. So this is an unsolved problem, and maybe nuclear physics could help on this. So I what people are thinking about this. Okay, so I will move on to more realistic galaxy model now, using this is big calculation actually, using hydrodynamics code plus including all the star formation and chemical enrichment as well. So I'm showing how Milky Way type galaxies form now. The first star was formed much earlier beyond Redshift 10, and the central high density clump appeared quite early time. That became galactic bulge now. And disk is small now, you can see, but this disk will grow with longer time, several giga-year time scale. So this is initial condition is cosmological. That means there are a lot of satellite galaxies nearby. So therefore a lot of mergers and interaction during the history. But there is no major merger in this case. If there is a major merger, it's not possible to keep this disk structure. So the bulge looks a bit bigger than observed, but this is the second best I could do in this case of calculations. So here I was showing the stellar luminosity of each point within the galaxy, but obviously I have the more full information, metallicity and elemental abundance of all star particles. So let's briefly explain, just very briefly, how we do this calculation. So we form a star particle from a cooling gas particle, assuming some very classical star formation criteria. There is a discussion, a lot of discussion about this, how to form stars. We don't know, but let's assume some process here. And then after the formation of stars, we follow the evolution of the star particle. Initial stage is stellar winds, massive stars are dying. Quark supernova produce alpha elements. Type 1a supernova produce iron. And finally, the remnant, black hole, neutron star, white dwarf remain as a star particle. Because now I'm talking about the simulation of galaxies, the galaxy consists of a billion of stars, but we can't use billion particles in a computer. So the one star particle have already 10 to the 4, 10 to the 5 solar mass. So the formed star is not a single star. We have to treat as an association of stars, assuming initial mass function. That's the caveat of this model. So Milky Way is pretty much all, but in a larger scale, in the massive galaxies, we also included the black hole formation from the first star and follow the growth of the black hole, and then feedback of the supermassive black hole by active galactic nuclei. That's heat up the interstellar medium and then suppress the star formation there. That process is also included in the simulation. The very first movie I showed just beginning of the talk was the massive star galaxy simulation with this AGN feedback. Milky Way, we don't need this supermassive black hole, and then let's stick to this star formation and chemical enrichment. So here is the metallicity map of the simulated galaxy. This is for my previous simulation about 10 years ago, but we have a very similar map also for the latest one as well. So you can see two gradients. One is a radial gradient. So if you look from let's on a face-on view, if you look from center to outskirts, the color becomes from red to blue. So that's the radial metallicity gradient. Central part is more metal rich. Also, on an edge-on view, there is a vertical gradient. On the plane, the most metal rich, plus above and below, metallicity decrease. So this is actually very much inconsistent with observed survey data, such as apogee, also for quantitatively consistent. They also find both radial and vertical gradient in the metallicity. But if I show the same figure for elemental abundance ratio, alpha to ion ratio, the figure looks a bit different. That's the alpha to ion ratio map. So there is a very strong vertical gradient you see on the right, but the radial gradient is very shallow. That's actually also inconsistent with the observed results that we can see, again, apogee and also Chinese Lamost survey. So that's the figure I showed earlier, alpha to ion versus Fe over H. The earlier I showed the model lines are only one line. So I said time goes from left to right. But now I'm talking now about the more realistic galaxy. So that chemical enrichment takes place inhomogeneously. So there is no one-to-one correlation between time and metallicity. But even though we see the very similar future now, so alpha to ion ratio is constant because of type 2 supernova, and then around FH -1 or so, there is a decreasing trend because of the delayed enrichment of type 1 supernova. In the simulation, there was this bimodal peak you can see with red color. And initially I thought maybe my simulation is not good enough. We don't see this bimodality in observation. That's I was thinking 10 years ago. But now Apogee also found very similar double peak in alpha to ion ratio. So maybe this simulation wasn't bad. It's actually captured the real elemental abundance future in our Milky Way. There is also low alpha sequence you can see as a trait that's also discovered now with satellite interaction. I can show the same figure not only for alpha to ion but also other elements. So that each panel now show a different element, alpha element, oxygen, magnesium, silicon, sulfur, and calcium. All have the same future. Some are odd Z elements, so you can see increasing trend toward higher metallicity. The same for manganese and copper as well. So when I overplot the observational data with dots, I go back and forth. I often do this in my talk. The agreement is quite good. Not only the absolute value, but also the scatter is well reproduced. So I'm not shifting anything here. So we use theoretical output of nucleosynthesis yield, and then we get this. There are a few notes. You see more points in the metal poor area. That's because observers are targeting to measure the metal poor stellar abundance. So that's why there are more points here. But in reality, most of stars in the solar neighborhood is located around the solar, just under the solar ratio. That's also seen in the simulation as well. So zinc is very important. So without hypernova, it's actually not possible to produce zinc as much as observed. And then with the assumption I explained earlier, it's just possible to get enough amount of zinc as observed. Let's move on to the neutron capture element, but with this hydrodynamical simulation now, focusing European abundance. So this is my former PhD student, Chris Haynes' work. So he included the neutron capture process one by one, switching off. And then so this is the same initial condition of Milky Way type galaxy, and then got this result. The simulation prediction is this small dark blue points. These are with the contour that's showing the number of stars at each population, and the colored points are observation data. So as you know, with only AGB, it's not possible to explain European abundance at all. Although there is some scatter you can see, some stars here at metal poor, there is a point here. So those are locally enriched by AGB stars inhomogeneously. So this high value, relatively high value at the European to iron ratio with the AGB, we didn't see in a one zone calculation earlier, but now we see some in this hydro simulation, even though not enough. So we switch on the electron capture supernova or neutron-driven beam, still not enough. With neutron star merger, however, it's possible to get uranium to iron 0 solar ratio at solar metallicity. But if you look at the scatter, there are a lot of stars, too many stars below the observational data. However, if we include magnetic rotation supernova, the scatter is decreased much and then very much consistent with this observed scatter now. So this is another, I'm saying the same conclusion now. The earlier it was with a simple one zone calculation, but this one with more big hydro simulations, and then we get the same conclusion. It is not possible to explode. It's not possible to explain observed European abundance only with neutron star merger. Magnetic rotation supernova is a very good candidate to explain the observation because of the short time scale. Okay, so I am almost running out time. So just briefly, this is another, my former postdoc, Fiorenzo Vincenzo, now at Ohio State University in the US. So he did a very detailed analysis of the simulated Milky Way galaxy. I showed the movie earlier. And we try to understand how actually this simulated galaxy evolved. So he measured, first of all, the star formation rate at a different location as a function of time. Also, he measured outflow and inflow rate. And we found, indeed, that the galaxy evolved inside out. That meaning star formation rate is highest in the center, but star formation rate becomes higher later on as a function of time in the outskirts of galaxies, propagate from center to outside. Always star formation rate is highest in the very center because of the number of stars is highest there. However, if when we measure the inflow and the outflow and then took the ratio between them, we found this universal relation. So the galaxy itself grows as a function of time. It's initially compact and it's grow later. So we also scaled with the galactic evolution scale. That's the D half. That's normalization of the size of the galaxy at each time. If we do that, always the central part of the galaxy, which is the left side, is this quantity is negative. So it's inflow driven. There is a higher inflow rate and lower outflow rate. The outskirts of galaxies, because of the shallow potential well there, inflow rate is low and outflow rate is high. So therefore, if we take the ratio, it's constant. We see the same relation both for the total mass and also metal mass as well. So the Milky Way type galaxy, the disk is very well self-regulated. It's regulated by physics, by gravitational force and then stellar feedback of supernova. So we also traced the motion of a gas particle as well as a function of time. So let's for 5 kiloparsec from the center, and then trace back where were they in the past. And then we found 2 sequences you can see. The first one is an inflow component. So that if we go back to the past, the distance becomes much larger. So it came mostly off plane, above the plane to the 5 kiloparsec on the disk now. And they also have metal poor and low alpha abundance as well. The second flow we see is this, the more along the plane. So it's happened much earlier, and then chemical enrichment is also ongoing. So supernova is also there. So they have high alpha and metal rich, and gradually flow toward the center. The speed is very small, 1 kilometer per second or so, 1 kiloparsec per second or so, but it's gradual radial flow we detected in the simulation. We do the similar analysis for the star particle as well. And let me tell you a very simple story. So go back to the, let's go back to the birth location of stars. We know where are they now. That's the present day radius on the y-axis. And then go back to the formation location. So we plotted against the birth radius on the y-axis. So if it's 1-to-1, meaning that those stars are on the disk plane and then they are just moving with a circular motion. But there is another sequence you can see here. That's the migration component. So let's say the stars located at 8 kiloparsec now, they are likely to be formed at 6 kiloparsec. That's the direct effect of migration. Our sun at 8 kiloparsec now could come from the 6 kiloparsec in the past. So I'm running on time, so just briefly, we also analyzed the kinematics of stars as well, and I found that the high alpha population tends to be old and also rotational speed is small. So that is consistent with the scenario of satellite accretion is important for the formation of thick disk. So this is a summary of, I don't think I have time to read out. So this is also ongoing work as well. So we would like to understand how bulge, halo, thick and thin disk can be formed. And then alpha elemental abundance ratios are very useful to test the physical processes in the galaxy formation theory. Let me just summarize up the point I would like to make today. So that's the first movie. I am not going to repeat this movie again, but it's actually possible to measure elemental abundance outside the Milky Way in other type of galaxies. So in this paper, also the same Fiorenzo Vincento's another paper, so we showed how carbon, nitrogen, oxygen abundance evolve in a different type of galaxies with different star formation histories. So in other galaxies, only light elements are observable. So we stick to CNO abundance. But using this combination, it's actually possible to constrain star formation galaxy in other galaxies. And then with JINA-CEE, it's possible to measure these three elements at once. So the next step is, I think, the extra-galactic archaeology. Chemodynamical structures of nearby galaxies and some medium redshift galaxies have been measured using an instrument called the integral field unit. There are lots of actually instruments in the world, and then lots of surveys are ongoing now. JINA-CEE is also have a same feature that can expand these observation data to high redshift. Chemodynamical simulation can explain the physical processes to tell the galaxy, to test the galaxy formation theory, as I showed today in my talk. And then we would like to know the true evolution of the creation rate of the elements across cosmic time. That will depend on the type of galaxy, also the location within galaxy. But the next step, using this big simulation, I would like to show in a few years' time, the periodic table in a different location of the universe. That's all. Thanks very much for listening.
Thank you very much, Dr. Kobayashi, for the very nice presentation. We have a few minutes for questions. Do you have any questions for the speaker? Please do not forget to unmute your microphones.
I see one question from Alex G on the chat.
Yep, we can hear you.
Okay.
And there are a few questions in the chat. Yep.
Yeah, if I can ask that question. So I guess the question is about the neutron star mergers in both the one zone and the chemodynamic models. And in particular, you know, if you take the, for instance, the LIGO estimated rate and yield for neutron star mergers and multiply them together, you get more than the solar abundance today. And so I'm wondering what the difference is between those numbers and the yields that are in this model.
Hang on. So the model prediction I am using is not so different from the observed rate. Well, that's dependent. Observation is 1 point, so the rate is very uncertain. So I am using binary population synthesis prediction, and then they are building a model to explain the observation. And I'm using the prediction, and the nucleosynthesis yield also theoretical prediction. The amount of R process elements is also consistent with the kilonova observation. But even though neutron star merger contribution is very small, but much difference in the rate and also theoretical yields. And then you also asked in the chat, I see the accretion disk component. Well, so I'm using the 3D simulation result by Senior Wanajou. So he has some structure in a neutron excess in his simulation. So all of the contributions are included, but he didn't split accretion disk or some other component. So so I think you are talking about more explicit additional accretion disk winds that is probably not included.
Okay, thank you.
There is also a question from Hendrik.
I have a question.
Yep.
Jackie, when you showed the periodic table, you had in thorium and uranium some green contribution, and if I understood it correctly, green stands for AGB stars.
Yep, that's mass loss
How
component.
do you do thorium and uranium in AGB
They
stars?
are not formed. They are trapped inside the AGB stars and released together with other AGB contribution. So this is the question I always asked. So this contribution includes stellar winds. So these heavy elements are not produced by AGB stars, but they are trapped. So they are produced by some other sources, and then they're trapped inside AGB stars and released when they die.
Okay,
yeah.
okay. And another question, there has recently been some doubts about electron capture supernovae. Initially, one thought they are between 8 and 10 solar masses. I saw one of your figures, you talk about 8.8 to 9 solar masses, if I'm correct.
Yep.
But there's also a bit doubtful if they really exist, depending on some recent experiments on electron capture rates. What would that change in your calculations?
So
if
they are not existed. So the electron capture produce, for example, 30% of strontium and so on. So it's not disaster. It's better if we have a small number of electron capture supernova. And then what you said is right. I am assuming it's metallicity dependent actually, very narrow range for the electron capture supernova. And the range comes from AGB, super AGB calculation. It could be much wider, 8 to 10 solar mass. In that case, electron capture supernova rates can be higher. So but anyway, they don't explain very heavy element production, but the rate is uncertain. Yeah. But what we are using relatively conservative, narrow range.
Okay.
Hendrik, do you want to ask your question?
Yes, hi. My question is about the comparison to observations. So you always show like a single element, how it evolves, but a lot of the measurements are actually abundance patterns, right? And they tell you a lot about what the right model for the origin is. Is that factored in? I mean, this introduces correlations basically. So all these observational data are correlated with each other in some ways. Are you factoring that in when you compare your model? And if not, is there a way to do this?
So the answer is no. So what we have been comparing to the number of stars with a given europium to iron ratio, number fraction over the abundance ratio. So that's only we are comparing to. And then, so in a very metal poor star, yes, there are some other models that trying to explain all elemental abundance pattern from light elements to very massive event at once with a single event, but that's we are not doing in this calculation. We could actually.
But what I'm saying is you not only have to produce the right trends for each element, you also have to produce the right patterns that are observed in some statistical way in all the stars. And I think the goal, for example, is probably a pattern problem. Yep,
that's very good point. Yeah.
So is there a way to do it?
So, yeah, it's like more multi-dimensional problem. So this should be possible in a statistical way. Yeah, we haven't done it yet. Yeah, that's very good point. Yep. Also now, not all elements are accessible, but with a multi-object spectra, it's actually possible to get multiple elements for the same number of target, huge number of sample. Yep, that's definitely a point. Although that very important element, uranium, thoriums are not measured with a large survey. So that's the very constraint for the very heavy element is still missing. We need to have a big survey with HSD, for example.
Yeah.
There are some people that have raised their... Oh. Sorry? Henrik?
I just said thank you.
There are some people that have raised their hands in the... here I see. We can start with Dr. Kian. He has a question.
Hi, Jackie. This is Yan Chen from Minnesota.
Hi.
Yeah, so I'm very much interested in your technical detail about the simulation. The size of your star particle in the chemodynamical part of the discussion. What is the size of your star particle?
10 to the 5 solar mass.
And this kind of particle is used for any kind of infalling units in building up of the Milky Way. Because there are things falling into the Milky Way when it's being built up, right? And so there are units like satellite galaxies and such. Those things also follow through.
Yeah, no. Well, that's limited by the computational power, and then we can't follow the growth within the particle. So yes, also the contribution from ultra faint galaxies. Alex G is listening now, but he's an expert. Those contribution is not properly included in the simulation yet.
Okay, so if I try to rephrase what you just told me, so in building out for the Milky Way, I understand you didn't consider any major mergers. So basically, all the process is just gas accretion.
No, well, the gas accretion triggers star formation, and also the supernova feedback suppresses the star formation. So it's also regulated by supernova feedback as well.
I understand that the dynamic detail, how you're treating it. I'm more interested in how the units you used to build up the Milky Way. So you have some kind of proto-galaxy, right? And then things are falling into it. So the subunits are not followed with detailed star formation history. You just treat them as gas inflow.
Well, it started from cosmological fluctuation with dark matter. So initially, it's very smooth, just dark matter fluctuation, and then gas follows. And then proto-galaxy, proto-dark halo formed, and then gas cooled inside the dark halo. Those processes are, in principle, all included with the limit of resolution.
Okay. All right. Thank you very much.
And I guess there is one more question from Huav Kassiv. I see
Yeah.
a raised hand. Yep, you can go ahead.
Yeah. So my question is related to the to Friedel Tillemann's question regarding the periodic table. I also didn't understand the lead. How come all of the lead comes from AGB stars?
AGB, yeah. AGB does produce red. That's already seen in AGB calculation. A lot of
Okay, but what about the contribution from actinides?
Actinides. So these are as I said, it's a mass loss. They don't heavier than the bismuth. So those are not produced in Roma stars, but they are trapped. They are produced by somewhere else, quark club supernova, neutron star merger. But those elements are trapped inside a Roma star. And then when there is a time delay, like a bomb. So when Roma stars are dying, those thorium uranium are released, come back to the interstellar medium. So it's not the product, not the production there. So this is releasing the elements from individual stellar side to interstellar medium.
So do they have to go through the AGB stars? They cannot be released directly from, for instance, neutron star mergers?
So the lot of, in an insurance function, observed one, a lot of Roma stars form, and they actually trap a lot of metals for a long time. So even those uraniums, thoriums are produced much earlier. They decay, of course, inside the star, but when they die, it's released. So that's the reason we included this stellar wind contribution in this figure. We also wanted to highlight how the mass loss is actually important. So it's, yeah, this is very confusing, I understand, but it's a mass loss component.
Okay, thank you.
Are there any other questions?
Maybe.
Oh.
Yeah.
Yes.
Question from a non-expert here. Thanks for the talk, Jackie. I wonder if you could backtrack your simulations as a prediction of what helium core masses of stars should be in our Milky Way. And I'm asking you that because this is a quantity that we nowadays can measure with quite good precision from astroseismology. And so is it possible for you to backtrack what you need to explain the galaxy from your simulations?
Yes, it is possible. So I assume a constant initial mass function, but the helium core mass depends on the metallicity. That is calculated self-consistently. So it is possible to predict. That's very interesting point.
Can I find these numbers somewhere in the literature? I'm trying to work my way into this field.
No, we have not published. We have not calculated that quantity yet. But that's very interesting. Can you drop me email again about the point?
Yes, I will.
Yeah, I'm very much interested in looking into that. Thanks.
Other questions? All right, then, let's thank one more time our speaker. Thank you very much, Chiaki, for your talk.
Thank you very much for listening.
And I hope to see you all in 2 weeks from now. Thank you very much, everybody.
Bye.
Bye. Thank you so much. Thank you.